Okay, let's have a look at an application of circular motion, and in this case we're going to look at the use of banking angles in turns. So if we remember back to our previous work, if we have a vehicle that's travelling in a circular path, so around a curve, the object will experience an acceleration inwards, which is our centripetal acceleration, caused by a centripetal force. Now we also noted that what holds this vehicle in this curve is actually the static friction between the tyres and the road. And we also noted that if that static friction, or the coefficient of friction between those two objects is zero, so in other words there's zero friction between the road and the car, our object or our car will just fly off tangentially to the acceleration that it experiences. So if we think about our roads, how do we ensure that our cars stay on the roads if we've got very low friction conditions? In other words, if we've got icy conditions or a very slippery surface. Well, it turns out it's quite simple. All we need to do is bank the curve as we're going around. So in this case, we've got our vehicle on top of our curve. We've got some angle theta. Let's now look at what actually happens. So the forces on this object, first of all, we've got gravity acting through the object. So we've got mg in our y direction, down. We've also got a normal force that's perpendicular to the surface of our bank. Now we can split this normal force, which we denote n or Fn, into its x component and its y component. And by similar triangles, theta down here on our bank is equal to theta up here. Therefore, in the x direction, we're going to get our normal force times cos theta, and in our x direction, we're going to get normal force times sine theta. Now, we know that we're not getting any net movement in the vertical plane, in the vertical direction, either up or down. So we know that this value here, Fn cos theta, must equal mg. So we can write that down, and then we can rearrange that for our normal force. So our normal force is equal to mg over cos theta. Now we're just going to leave that for a second, and we're going to see what happens in the x direction. Now we know in the x direction, as this vehicle travels around this curve, it's going to experience centripetal acceleration caused by a centripetal force. Now we also know that the only other force acting on this is our Fn sine theta. Therefore, this must be equal to our centripetal force, and if we substitute in centripetal forces mv squared over r, we get this particular function. Now we can substitute in our normal force up here for mg over cos theta. So we've got mg over cos theta times sine theta. Sine theta over cos theta is equal to tan theta. And we notice that we've got an m on both sides, so we can cross them out. So we get tan theta is equal to v squared over gr. And we can rearrange to give us a banking angle for this particular curve to be equal to the inverse tan of the velocity of the car over gr. Now there's two things to note with this. First of all, this equation is independent of friction. So if we had an icy road and we wanted vehicles to travel at 50 kilometers an hour, we work out the angle as the optimum angle for those vehicles to travel at, and we build that road on a slight curve. And that will ensure that the vehicles don't slip out, they won't slip out or they won't slide out as they experienced here. Now it's also interesting to note at this point in time that if the vehicles travel faster than the recommended velocity for that angle, they will still slip out, but if they travel too slow for it, they'll actually slip down the incline as well. So we call this angle here an optimum angle. Now the second thing to note is if we made theta 0, in other words we flattened out this incline completely, we'd find that unless we have a frictional component, our velocity will also equal 0. In other words, if we don't have any friction, we once again find that that vehicle will slide out as it did before. So let's look at this in action now in a problem-based question. Let's say we have a car negotiating a turn of radius 80 metres, and we want to know the optimum angle for this curve if the speed of the car is 12 metres per second. And then secondly, what happens if we change that angle to 20 degrees? What happens to the speed of the car, or the optimum speed of the car? So the first thing is we draw our diagram. We have a curve of 80 metres. We have a banking angle of theta, and we have a velocity of 12 metres per second. First thing we're going to calculate is our angle. And we know from our equation that theta is going to equal the inverse tan of v squared over gr. We put our numbers in, so 12 squared for our velocity over 9.8 times 80 gives us a banking angle of 10 degrees. Remember, this is the optimum banking angle. If we shift it up or shift it down, and the vehicle's travelling at 12 metres per second, the vehicle may slip up or slip down. And we see that because there is no friction with the vehicle. Now, what happens if we change this angle to 20 degrees? We want to know what's going to happen, or what the optimum velocity is for that particular vehicle. So we're going to rearrange the equation now for v squared, and finally for v. So v is going to equal the square root of gr tan theta. We put our numbers in, and we find that the optimum speed for our vehicle on a bank of 20 degrees has now moved up to 17 metres per second. So what this is telling us is that if we increase this angle, we need to actually travel around that curve a lot faster. And obviously if we decrease the angle, we can travel around that curve a lot more slowly. And that makes sense, because if we tighten the, if we increase the curve, we know that we'll slip down. In other words, we'll slip down here if we don't have enough speed. So that's how we use, and that's how banking angles are actually used.